Okay, so welcome everyone. Good afternoon. This is the ninth interactive session for the NPTEL course Experimental Physics First. The course instructor is Professor Amil Kumar Das from IIT Kharagpur, and I am Rinalini, PMRF Research Scholar, School of Physics, University of Hyderabad. So as you know, this interactive session happens every Saturday from 3 p.m. to 5 p.m. and this is the ninth interactive session. Let's start with today's session. Let's have a recap of last week's contents that we covered. Last week we talked about the theory and the experiment of coupled pendulum and understood what is coupled pendulum, how is it different from simple pendulum, as you can see in the figure here, and what are the in phase and out of phase conditions for coupled pendulum, and what is the resonance condition. We had derived these conditions and understood these things. Another experiment that we did was of the compound pendulum, where again we did the theory, understood what is a compound pendulum, and this is the working formula that we had derived and understood how the experiment has to be done to find out the time period for a compound pendulum as seen in the figure here, and also did previous year and other problems based on the concept of compound pendulum. Another experiment 8, we understood what are standing waves, how they are generated, what are the different parts of a standing wave, be it nodes, antinodes, and how we can find out the frequency of a standing wave. And of course, again, the experiment we understood and then did questions based on the concept of standing waves. Also, we understood linear expansion of metal, the concept of linear expansion of metal and the constant shown by alpha, this is which denotes the linear expansion. It is the linear thermal expansion coefficient, and it's given by this formula, where in the numerator it's change in the length, and denominator it's the original length times the change in temperature. So alpha is the linear thermal expansion coefficient, and we understood what is the experiment, how to perform the experiment to find out this the value of alpha, and also solve some questions based on this. So these were the things that we did in last session. Now for this session we'll start with again it's something about the heat absorbed or released by a body. So it's about the thermal property of material. So the name of the experiment is determining the coefficient of thermal conductivity of a bad conductor. So actually, what's the thermal conductivity? As we knew earlier, we had discussed what is electrical conductivity, that how good is electrically good or bad is a conductor, how easily the electrical current can pass through that conductor, how less is its resistance. So that we used to call as a good electrical conductor. The same way, there is something known as thermal conductivity of a material. So thermal conductivity of a material is a measure of its ability to conduct heat. As in case of electrical conductivity, we talk about how easily it can conduct electric current. The same way, when we talk about thermal conductivity of a material, we talk about how easily it's able to conduct heat, and that is known as thermal conductivity of that material, and the SI unit is watt per meter per Kelvin. So we will not do any derivation, but we will start with directly with the formula that have been derived by scientists, and we will directly use it to understand some experiments. So there is a law associated with heat conductivity, thermal conductivity, which is known as Fourier's law for heat conduction, or Fourier's law for heat conductivity or thermal conductivity. So what this law says, according to Fourier's law, the heat transfer. So this is the, if I represent the rate of heat transfer by Q, okay, so I'm calling it rate of heat transfer, means it's heat transfer per unit time. Okay, so this is rate of heat transfer. So according to Fourier's law, rate of heat transfer is actually is proportional. The law says that this is proportional to the area of cross section of the material that we are considering here. Okay, inversely proportional to the thickness of the material. If thickness I represent by small d, then it's this, and proportional to the temperature difference. So if we talk about, which we'll be using in experiment as well, if we talk about a disc, a cylindrical disc, if we talk about, okay, then it has some thickness d, it has some radius r, from which we'll get the cross sectional area, right, pi r square it will be. And if due to some means we are supplying heat to one side of this disc, say one side the temperature reaches T2, another side it's T1, then the rate of heat transfer or rate of flow of heat from one side of this disc to another side will be given by this expression. It will be proportional to the temperature difference, this inversely proportional to the thickness of the disc, proportional to the area of the disc. This is known from the Fourier law, and since there should be a constant also, this constant we show by K, which is called thermal conductivity that we were talking about. That thermal conductivity is a property of a material. So this K is the constant called thermal conductivity. Okay, and the unit is watt per meter per Kelvin. So this is Fourier's law of heat conduction. Now okay, so let's talk about one more thing. What is heat capacity? So heat capacity is defined as the amount of heat energy required to raise the temperature of a given quantity of matter by 1 degree Celsius. So if I have some object, some material, maybe either we can consider some amount of liquid in a beaker, or even it can be a solid material, some some wax, say some wax or candle or something is there, and if we supply heat to it, it will start melting or its temperature will increase, depends what kind of material it is. So heat capacity of that material will be defined as amount of heat energy required to raise the temperature of that particular amount of material by 1 degree. So here we are not specifying the how much quantity, we are just saying that whatever material I have, to increase its temperature by 1 degree centigrade, how much heat has to be supplied, that will be known as heat capacity of that material. Now there is another thing also, that is specific heat capacity. So what do we mean by specific heat capacity is the amount of energy needed to increase the temperature of 1 gram of a material by 1 degree centigrade is known as specific heat capacity. So when we are talking about heat capacity, we are not defining the amount of material, but when we are talking about specific heat capacity, then we are defining the amount of the material, which is to be 1 gram. That's why this value is constant for a particular material. So and the unit here is joule per kg degree centigrade, or we can also define it as joule per kg and degree, Kelvin. Okay, so what is the experimental method to determine the coefficient of thermal conductivity K So the method is called least disk method. Okay, least disk method. It is given by some researcher Lee. I don't know the full name, but yeah. So this least disk method, as the name suggests, we use a metal disk. When we use, I mean, sorry. So we want to find out least disk method is specifically used actually for determining the thermal conductivity coefficient for a bad conductor. There are other methods which are used for which are more convenient or more appropriate to be used for good conductors, but for a bad conductor, or you can say for a thermal insulator conductor, also like thermal conductor we are talking about, right? So a bad conductor or a thermal insulator, to find its thermal conductivity we use least disk method. So in what we do in this method, if you see in the figure here, this is a stand. So this disc that we see in pink color here is the insulating material that we are interested in, whose thermal conductivity we want to find out. Now on as it was shown by the professor in the lecture video, that it was there he had taken a rubber material in the form of a disc. So this is also some sort of insulating, thermally insulating material. On one side there is a metal disc. This is a metal disc. Here it's written brass, so it's a metal disc. This one is the metal disc 1. Now this is metal disc 2. These are mainly to create temperature difference. So what we do is, in this downward also we have kept one thermometer, in upward also we are putting a thermometer to measure the temperature difference. Now how we'll create the temperature differences? First both will be at room temperature, then at the top metal disc we'll keep another container in which we'll supply steam. Okay, the gas or the steam, boiling steam, that will conduct and will increase the temperature of this metal disc, and thus it will increase the temperature of one side of this insulator. Because it's an insulator, there will not be conduction, or it will be, because it's a bad conductor we are calling, because there may be very small conduction but it's almost negligible. Anyway, so at one side there will be higher temperature, another side it will be lower temperature. So from the Fourier's law we have understood that the rate of heat transfer steady state, we understood, from the law we understood this, right? That rate of heat transfer is given by this formula. This T2 T1 depends which you are taking higher. If we are taking this higher temperature to be T2, as it was given in the experiment also, so I'll take it like this, then we can we can subtract this higher and lower, and in numerator we will get the thickness of this. From this you can understand that the thermal conductivity, if I rewrite this equation, it will be given by heat transfer rate times thickness divided by temperature difference times the area of cross section. Either I can write A, or it will be pi r square. So in this experiment what we are doing is, on one side we'll increase the temperature of the insulator by supplying some sort of heat. Here we are using the steam chamber for that purpose, and we'll measure T2, we'll measure T1, thus we know the temperature difference. We we can measure the thickness of our material of interest, or this insulating material. Its radius also we can measure using slide caliper or scale, depending on its which is suitable. But this Q is unknown. Right now we don't know this, what is the rate of heat of transfer, but what we understood from specific heat capacity, that it is the amount of heat required to raise the temperature of 1 gram of material by 1 degree centigrade. From this definition we understand that this rate of flow of heat, this rate of flow of heat will be given by mass of the material times the specific heat capacity. If I denote it by S, then specific heat capacity times the rate of change of temperature per unit time. So this will be the rate of heat transfer. Okay, equating this one, no, I mean putting the value of Q from 2 to 1, we will get thermal conductivity is equal to ms dt by dt. Here this is the temperature difference, this is the time, in how much time the what is the change in temperature. This times thickness divided by temperature difference pi r square. And this, for this actually what we were doing, this was for T1. So what is the, like, how the temperature would change for T1 disk. For that, if you check the experiment as given in the video, so we were supplying steam to that, and then we remove it and see at in what time how its temperature will decrease. From that we get this dt by t rate. Okay, so from this is the working formula for this experiment, and from this we will be able to find out the coefficient of thermal conductivity for this bad conductor that we have taken. So this is the least disk method. Now there is another experiment that was discussed, which is determining electrical equivalent of heat. So first let's understand what's this electrical or mechanical equivalent of heat. It is also known as Joule's equivalent of heat. So it's defined as it's denoted by capital J, and this Joule's equivalent constant or mechanical equivalent of heat is defined as the amount of work required to produce 1 calorie of heat. So this Joule's constant, Joule's equivalent constant, is whose value is 4.2 joules per calorie. It means 4.2 joules of work is required to produce 1 calorie of heat for any material. Mathematically 4.186, or you can round it off to 4.2. So mathematically 4.186 joules of energy is required to raise the temperature of 1 gram object by 1 degree centigrade, or to produce 1 calorie of heat, and this constant is known as Joule's equivalent constant or mechanical equivalent of heat. Now the experiment that was demonstrated, there actually we were calculating electrical equivalent of heat. So what we were doing, so this joule can be defined as work done. It is actually the ratio of work done and heat generated form, and the work done could be mechanical or electrical. So in this, specifically in this the experiment that was demonstrated, there we had used electrical work by supplying electric current. We had used electrical work to generate heat, and then we tried to calculate the value of Joule's equivalent constant. So let's understand what is a calorimeter, because we'll be using a calorimeter to perform this experiment. So calorimeter is nothing much of a big thing. It's just a container, a metal container, usually brass or copper, with a stirrer The stirrer is because this calorimeter is filled with usually water, and there is some heating material, some hot material also kept inside, and to insulate it from environment, we cover it, and thus this whole setup, I mean we cover it, thus it becomes difficult to stir. So I mean mix the liquid properly, because as I said, if we put some hot object inside this, then we want to measure the temperature of this at equilibrium of this liquid. For that we put a thermometer, but if the thermometer is near this hot body, then its temperature will be different, but the temperature away from this hot body will be less. So we use this stirrer to stir the liquid continuously so that we get homogeneous temperature. I mean the temperature everywhere inside is homogeneous, and then whatever measurement we do for temperature, so this is a thermometer, and so that whatever we measure is correct value. So a container with the stirrer is what is called as calorimeter. And yeah, you can see this is thermometer, this is stirrer, and we insulate it. So this setup is called calorimeter. Okay, so this as I was saying, that in this experiment it was demonstrated that we were using electric work to generate heat, and then we were trying to determine the Joule's equivalent constant. Since we know that work done when current flow in a wire, work done is given by the charge times the potential difference. Since we know charge is current times the time, because current is flow of charge per unit time, so charge is current times the time times the voltage difference. We also okay, so electric work, which is W, this can be written as Q times V, or I times T times V, or if I want to write only in terms of potential difference, then it will be V square T by R. From Ohm's law we know that V is equal to IR, right? From there we can write it like this also, or if I only want to write it in form of current, then I will write it I square RT. So these are different forms of writing the electrical work done. In this experiment, what we are doing is, actually there is a container, water container, and we are the water container. Okay, this is the container, it contains water, and we are supplying electric current through a resistor. This is a coil, we are applying voltage, and there's a current is flowing through this resistor coil. And since we know there is current flowing, means there will be heating, that heat will be released by this coil and absorbed by the water, and by measuring the raise in the or the increase in the temperature of water, we will try to find out this Joule's equivalent of heat. Okay, so as we talked about heat capacity, and that so as we had discussed, that specific heat capacity is the amount of heat required to raise the temperature of 1 gram of an object by 1 degree centigrade. So by this definition we can write the amount of heat as the product of mass. So if specific heat capacity of a body is known, then we can write the heat that is supplied as the product of mass of that body times the heat capacity. Either we can keep we use sometimes the symbol C or S, it depends, we can use anything, times the temperature difference. So this is the expression for heat supplied for that body. So in this calorimeter, where it consists of the container and stirrer setup, the heat that is supplied to the water will be the mass of water times the mass of the specific heat capacity of water plus mass of the calorimeter, because it will also absorb some heat, times the specific heat capacity of calorimeter. So this together, and then the temperature difference. So when the current is given, it will heat up the water, and after some time the temperature will get to an equilibrium point. From then we'll get this temperature difference. So this will be the heat transferred to the water. So when we perform this experiment, we will be able to calculate the final temperature, initial temperature, mass of the calorimeter and water we can measure before performing the experiment, and the specific heat capacity of water, and this whatever the calorimeter is made up of, whichever material. So for that material, these specific heat constants values are known. So we can use that to determine the heat supplied. Thus, so again, what we want to calculate is J, which is the ratio of work done and heat. Heat we will be able to determine from this thing. Now, electrical work, we can whatever voltage we are supplying, and we'll connect it to the emitter and see what is the current we are supplying, and what if we should actually put the known resistor for what time we are supplying the current. Depending on that, we will be able to calculate the electric work. Either we can supply the voltage and then we can measure the current, or we can supply the constant current and then measure the voltage. Any of these methods is fine, but ultimately from this we will be able to determine the electric work. Now H is known, W is known, thus from this doing these two things, we'll be able to find out J, which should come about 4.2 joules per calorie. So this was the experiment to determine the electrical equivalent of heat. Now the next experiment, experiment 12, was about determination of specific heat of given solid metals using Dulong-Petit's law. So first let's understand what is Dulong-Petit law. Dulong-Petit law states that the heat capacity for many solid elements is constant and approximately equal to 3R, where R is the universal gas constant. So what Dulong-Petit law is telling us, that heat capacity, that we understand heat capacity is the amount of heat required by a material to increase its temperature by 1 degree centigrade, right? So it's telling that heat capacity for many solids, this law is applicable to many of solid elements, not all but mostly. So heat capacity of many solid elements is constant. So it's it's not depending on what type of material it is. Mostly its value is constant and is equal to 3R, where R is the universal gas constant. So ultimately what it's telling, that it doesn't matter what is the nature of the substance. So regardless of the nature of substance, the specific heat capacity, C or S, as I told, we can denote it with C or S, anything is fine. So specific heat capacity of a solid element measured in joule per Kelvin per kilogram is equal to 3R per M. If we are talking about specific heat capacity, then you know we need to divide by mass. If we are just talking about heat capacity, then the value is 3R. Okay, where here also what we mean is that R is gas constant, M is molar mass, and heat capacity per mole for many elements is 3R. So this is Dulong-Petit law. Now the experiment that was performed by the professor in the video lecture to verify Dulong-Petit law, there what we had done was, we took again a calorimeter and we took a calorimeter. Again, you know what is a calorimeter, right? It's something like this. Just let me see. Recording is going fine, right? Okay. Yeah. So this is again the same kind of setup, the same calorimeter, and what we'll do is we'll take some material, say some cubic, and it can be any shape, doesn't matter. Again, nature of substance doesn't matter, shape, nothing, these things don't matter. So it could be any, the shape of the body could be anything, it could be any material, but we'll increase its temperature. How we'll increase? Say it's a metallic, it's a metal object, and we'll place it in a boiling hot water. So it will, due to conduction, its temperature will increase. Now this has become hot because I placed it in boiling water. Because I placed it in boiled water, so its temperature has increased. In this calorimeter also I have some water at room temperature. Okay, and then I take this hot water out of this boiling water and keep here. Now there will be heat transfer, heat exchange between this hot metallic body and this cold water. Again from the end, yeah, there will be heat transfer. So we know that heat, what is the relation between heat and specific heat capacity. In terms of specific heat capacity, when we write, it's mass times specific heat capacity times the temperature difference. That will be the heat transfer. So heat transfer or heat released by the metallic body will be equal to the heat absorbed by this calorimeter plus water. So both the calorimeter container and this water will be absorbing the heat, and the metallic body, which was hot, that will release the heat. So there will be heat transfer between these two things, and the amount of heat that is released by this body will be the same, the heat that will be absorbed by this calorimeter plus water. Now H released will be written as mass of that metallic body, its specific heat capacity, either S or C, whatever we want we can write, and the temperature difference. So how we will get to know this temperature difference? So whatever if I boiled it to some temperature, I kept the thermometer here, okay, and from this I measured the temperature of water. I'll consider same as the temperature of this body. So that will give me the value of T2. After I keep it here, and after some time T, the heat transfer will stop and equilibrium temperature will be attained. Again here also, if I'll keep a thermometer, I'll be able to find out the T equilibrium after time T, not immediately, after time T, when it reaches equilibrium. That time I'll be able to find out the T equilibrium temperature. This will be equal to the this mass of water, including the specific heat capacity, plus this water equivalent of calorimeter. Means again this specific heat capacity of the calorimeter times its mass, it includes this. That's why it's called water equivalent of calorimeter. This times the temperature difference. What will be the temperature difference? So its initial temperature was less, but final temperature is higher because it has gained the temperature from the hot body. So equilibrium temperature will be higher, and its initial temperature, let's call it T1. Maybe it was at room temperature or maybe it was cold, whatever, but equilibrium temperature will be higher. So this will be the expression for heat transfer. I mean, these two things we can equate, and since all these quantities will be known, we can find out the heat capacity from this. Mass is known, these temperatures are known. Mass of water, water equivalent of calorimeter, these all things we can measure, and from this expression we will be able to find out the specific heat capacity of this hot body, which we had heated, and its specific heat determining, because our experiment was about determining the specific heat of the solid body, so we will be able to calculate from here, right? This whole expression divided by, let me write, so this is mass of water plus water equivalent of the calorimeter times the temperature difference. Temperature difference of what? This is temperature difference of, this is temperature difference of water plus calorimeter system divided by mass of, this is the mass of the hot body, and this is the temperature difference that we measure here, and for the body. From this expression we will be able to calculate the specific heat capacity, and we will be able to verify Dulong-Petit law, because it should come equal to 3R. And since R is the gas constant, as it's a constant, its value is known. Its value is 2 calorie per Kelvin per mole. And since the specific heat capacity value should come out to be 3R, means it should be almost equal to 3R, means a value of R is 2 calorie per Kelvin per mole, means this would be 6 calorie per Kelvin per mole. So after experiment, this should be the value we should be getting. So this was this equation that we have written here, that the amount of heat transferred from the hot body and the amount of heat absorbed by the calorimeter plus water system. This equation is known as law of heat transfer of calorimetry, or law of calorimetry. Anyways, moving on to the another experiment. Okay, this experiment is known as determination of Seebeck coefficient of thermocouple. So first let's understand what these keywords mean. So what is a thermocouple? A thermocouple is a device that measures temperature of any body or any system by using thermoelectric effect. So thermocouple is a temperature measuring device. Like we use thermometer, we keep one end to the insert the system, and there we see the rise of mercury, right? From the where the mercury level is, from there we can read what is the temperature of that body. Same way, here instead of using mercury, some other working principle is used, which is thermoelectric effect. So thermocouple is also a device that measures temperature, but instead of mercury, it's utilizing thermoelectric effect. Now let's understand what do we mean by thermoelectric effect. So thermoelectric effect is conversion of temperature difference into electric voltage and vice versa. This happens when electrons move from hot to cold region in an object, generating an electric current. So thermoelectric effect is the direct conversion of temperature difference into electric voltage. So if there is temperature difference in a body, then it means there will be electric voltage difference. If there is temperature difference between the two ends of a body, that means there will be voltage difference between those two ends, and vice versa. This is known as thermoelectric effect. It depends on the kind of material we are talking about. There are three types of thermoelectric effects. Three types of thermoelectric effects that are known. First is Seebeck effect. So Seebeck effect is a phenomenon in which a temperature difference between two dissimilar electrical conductors or semiconductors produces a voltage difference between the two substances. So Seebeck effect is the effect in which temperature difference between two dissimilar electrical conductors. Dissimilar means different. So if you see here, this is actually, you can say it's a thermocouple. Here is shown by a rough sketch of how a thermocouple is actually, that this is wire of type A material, this is another wire of type B material, and these both are connected at this particular junction. For time being, just we are naming it as hot junction, and there is a voltmeter attached on another side, and here again they have a common junction which we are calling cold junction. So what Seebeck effect is that when a temperature difference between two different electrical conductors or semiconductors is happens, there is a voltage difference between these two substances. Because this material, this particular wire is of different material, this wire type wire B is of different material, their heat conductivity will be different, their electrical conductivity will be different. Because of that, if I am heating this common junction using some form of heat, the heat conduction of both wires will be different, since they are made up of different materials. Since their heat conduction will be different, here I am supplying heat, right? So the electrons at this particular junction, which is common between both wires, the electrons here will gain that energy and they will try to move, right? They will try to move in this also and in this wire also. So depending on the heat conductivity, thermal conductivity of these wires, in one wire the electrons will be able to move fast, in another they will be slow, and where they'll move faster there will be lower potential energy. Because see, if imagine just like in this, their thermal conductivity is higher, the electrons are moving faster and they all accumulate here, there will be negative charge here. Here they are moving slower, this will be less negative charge here, means this will be at higher potential compared to this end. So there will be a voltage difference as well generated here because of this difference in thermal conductivity of these two wires. So this is what is known as Seebeck effect. Now there is a reciprocal of it, which is the Peltier effect. So Peltier effect is a thermoelectric phenomenon that occurs when electric current passes through a junction between two dissimilar materials, causing one material to heat up and the other to cool down. So when electric current passes through, again consider that there are two different type of materials attached at one end, and now we are passing current through this. So because of difference in electrical conductivity, there will be heat generated, and this is reverse of Seebeck effect, known as Peltier effect. There is third effect known as Thomson effect, which occurs when an electric current flows through a homogeneous conductor, but that conductor has temperature gradient along its length. So there is some sort of conductor which is not uniformly at same temperature. It has temperature gradient, means some point the temperature is something else, at some point the temperature is something else, like that. In this kind of conductor, if I am passing current, then in other words, in one part of conductor is at higher temperature than another part, and an electric current passes through it. So in that case, what will happen? Some particular part will absorb the heat, other parts will release the heat along different points of this length. So this is known as Thomson effect. So these three kinds of thermoelectric effects are seen in any body. So this thermocouple experiment based on this was performed in one of the lectures, if you will see last week's lectures, where we wanted to find out the Seebeck coefficient. Seebeck coefficient for that particular thermocouple. The Seebeck coefficient is actually the ratio of the voltage difference that we measure to the temperature difference across the two ends of the thermocouple. The working formula is this: negative gradient of voltage to the ratio of the temperature difference. Seebeck coefficient, its SI unit will be microvolt per degree centigrade, since the voltage difference is very small. So usually for 1 degree centigrade temperature difference, the voltage is in microvolts. The voltage change is microvolt. So this is the Seebeck coefficient formula. So how we'll perform this experiment? Okay, let me draw here itself, or I'll take, just let me take one slide. So for this, actually, again, from scientifically it's known that general expression for thermo EMF, general expression for thermo EMF in terms of temperature is given as, this is thermo EMF generated because of heat. It's given by AT plus BT square plus CT cube and so on, where A, B, C are constants and they depend on the kind of material we are talking about or the type of thermocouple we are considering, and this T is actually the temperature difference. So temperature of coil you can call it, and the reference temperature. So this small t represents the temperature difference. So if we ignore the higher order terms and substitute the value of small t, then we'll get the thermo EMF will be equal to A times temperature difference here we'll ignore the higher order terms. Okay, yeah, we'll just ignore the higher order terms. So this will be the expression, and from our experiment, if of thermocouple, again one end we'll heat by any means, by providing steam, or if you remember in the experiment as demonstrated by professor, the experiment for thermocouple, he was heating one end, like there was, sorry, so he had kept in one container boiling hot water, right? In another place he had kept ice. So one end of thermocouple he kept here, another end of thermocouple he kept here, and then we were measuring voltage, right? So and there was thermometer here, there was thermometer here. So temperature difference we know, voltage we could measure from here, thus we know the voltage difference, we know the temperature, we can plot. We actually need to see how their plot is changing. It could be linear, it may not be linear also, but the slope from here, if this higher order terms are negligible, then we may get linear slope, and from this we will be able to find out this Seebeck coefficient, yeah, S. So this was that experiment. For details of experiment you should refer to the video lectures. Here we are just having quick review of the theory aspect, and later we will be solving questions based on these concepts. So these were the theory for the experiments that were performed in the video lectures of last week. And now, okay, there's one more thing, but details of this particular thing will be discussed in the upcoming week. But because it was introduced, so let me tell you about this also. So this experiment will be about theory and demonstration of platinum resistance thermometer. So as we are talking about different kind of thermometers, all our life we have seen the mercury based thermometer, right? Just now we understood there is something known as thermocouple also, which is also kind of thermometer, but it works on the basis of thermoelectric effect. There is another kind of thermometer, which here we are talking about platinum resistant thermometer, which is a piece of platinum wire which determines the temperature by measuring its electrical resistance. So one mercury thermometer, we all know, as the temperature increases, mercury expands and we can read the what is the temperature. Another is thermocouple. So depending on the temperature difference, we get the voltage difference. So we can from conversion from there we can read, if we know this Seebeck coefficient, we can convert the voltage difference to the temperature difference, and from there we can determine what is that, read the temperature. Basically we can measure the temperature. This third temperature measuring device or instrument that we are talking about is this PRT, or platinum resistance thermometer, which uses a piece of platinum wire. So platinum wire, as you know, platinum is a metal. Its symbol is PT, I think. Platinum is a metal and it's very sensitive to its resistance of platinum is very sensitive to temperature. As we know, for metals, as the temperature is increased, their resistance increases, right? Because the atoms in the metal, they get energy, they start vibrating, they start colliding more and more with the electrons passing through them. So electricity is passing, that means electrons is passing, and they start getting more collision happens with the vibrating atomic cores. Because of that, resistivity or resistance of the metal increases. So that's why we are using here a metallic wire, specifically platinum, and here we will be able to measure the temperature depending on the electrical resistance. So inside this actually is platinum. We have this in detail, actually we'll understand next time, but ultimately what I want to tell you, the coil of platinum wire is here, and when we'll keep this tube thing inside any kind of material, say some water is here, and I don't know at what temperature it is, but if I keep this PRT inside, it has some electrical connections actually. So it should be immersed inside the water, and I'll connect it to my electrical component. There I'll see what is the voltage, what is the current of the platinum wire, and depending on this we'll be able to find out, since from Ohm's law I'll be measuring voltage, I'll be measuring current, and I'll be able to calculate resistance of this platinum wire. And depending on, since we know that at what temperature what is the resistance of platinum, if we know this scale or that range, then we'll be able to tell if we calculate R to be something, say R1, and from the scale we know that R1 means the temperature is T1, then we'll be able to say that the temperature of water is T1. So this is the third way of measuring temperature. So in detail we'll be talking about this PRT in next session. But now let's do questions based on the theory for the experiments that we discussed till now. So first question is, a metal rod of thermal conductivity K and length L, area of cross section A is maintained at temperature difference of theta 2 minus theta 1 between two ends. Now if we consider the thermal current similar to that of electric current, then thermal resistance can be written as. Okay, so the question is, we have a metal rod. So we have a metal rod of thermal conductivity K. Its length is L, area of cross section is A, and it's maintained at temperature difference theta 2 and theta 1. So assume one side temperature is theta 2, another side temperature is theta 1. Then temperature difference will be theta 2 minus theta 1 as given here between the two ends. Now if we consider thermal current, heat flow per second, if we consider it as thermal current similar to that of electric current, then thermal resistance can be written as. Okay, so let's do a comparison. Like we know that if there is a wire, okay, wire is also again we consider cylindrical, right? So there is a wire, and when there is potential difference across that wire, then only the current flows in that wire. This we know. And the expression for current is from the Ohm's law, potential difference divided by the resistance of that conductor or that wire. Now we know resistance, expression of resistance is rho L by A, or I can write it as L over sigma A because resistivity is reciprocal of conductivity. If I insert it here, it means I will be V A sigma by R, right? The same way for thermal conductivity, we had understood that there is something called heat transfer rate, right, which is given by thermal conductivity constant times area of cross section times the temperature difference. In electrical conductivity we talk about this V is actually the voltage difference, right? So this V is, I'll write it like this, it's V2 minus V1 divided by R. For in case of electric current, for flow of heat transfer, the expression is this divided by L, okay, or I can write it like theta 2 minus theta 1 divided by, if I take this also to denominator, then I will get L divided by Ka. And when I'll compare these two, this equation 1 and this equation 2, we have been asked to find out thermal resistance. Okay, so what equivalent we can see here is, since this potential difference is equivalent to temperature difference, that means the resistance is equivalent to this value. This resistance is equivalent to thermal resistance can be written as, or wait, I think from this it should be, wait, if I equate these two, like L by Ka and R by sigma A, but yeah, okay, these are different things. Only if we compare, I think the resistance, either we can take this whole L by K, either it will be L by K, I think, yeah. If we are considering, because it's given metal rod if we take cylindrical, and wire also if we consider cylindrical, then question of area of cross section comes, and in that case I think we can say that resistance, I think in that case we can say resistance is L times it will be this, but it's not there in the option. Okay, anyways, so I think still we can say that the correct answer could be this. This just a similarity thing they have tried to assume, but yeah, I think thermal resistance can be considered to be L by Ka. This should be the answer. Comparing this equation 1 and equation 2, we can say this. Okay, so the next question is, find the atomic weight of material having a specific heat capacity equivalent to 600 joule per Kelvin per kg. So specific heat capacity value is given 600 joule per Kelvin per kg. We have to find out atomic weight of the material. Now if we recall that Dulong-Petit law, then we know heat capacity of a material is given by 3R by M. Specific heat capacity is given by 3R. Okay, if I represent specific heat capacity by S, then specific heat capacity is given by 3R. Heat capacity will be given by 3R by M. Here, from this, M, the value of M I can calculate, atomic weight I can calculate, which will be 3R by C. Now, 3 times value of R actually is 8.314 joule per kg per, sorry, 8.314 divided by heat capacity is 600. If I'll calculate this, I'll get how much? 3 times 8.314 divided by 600, it is 0.04157 kg per mole, which if I put it in gram, then it will be 41.57 gram per mole. This will be the answer. Okay, next question. The thermo-EMF equation for a given thermocouple is, thermo-EMF expression for a given thermocouple, if is given by this, then the thermoelectric power of this couple at 100 degrees centigrade. So we know that power will be this derivative of this thermo-EMF with respect to time. So d by first derivative with respect to time of this thermo-EMF equation, 15t minus 0.03 t squared. Okay, derivative will be 15 minus 2 times 0.03 t. Now this value of power at 100 degrees centigrade means value of power at 100 degrees centigrade means this, we'll substitute this was not time actually, sorry, this was temperature. Yeah, in this, if you recall, in this expression we had earlier written, right, thermo EMF in terms of temperature difference is given by AT plus BT square and so on. So here T was not time, T was the temperature difference. So yeah, I made the mistake. T is not time, T is the temperature difference. So the derivative that we did, that is with respect to temperature. So this is the derivative. Now we need to find out the electric power for this thermocouple at 100 degrees centigrade, means that T is equal to 100. So when I will substitute T value 100 here, what we'll get is 15 minus, this will be 3, means 15 minus 6, that will be 9, right? It will be 9. So the answer will be, this was in microvolt, this was in microvolt, so microvolt per degree centigrade, microvolt per degree centigrade, sorry, yes, 9 microvolt per degree centigrade is the correct answer. Now the next question, the process of heat transfer in which heat is transferred with actual migration of medium particle is known as what? So which of these heat transfer process, in which of these heat transfer process actual migration of medium particle happens? So what is conduction? Conduction happens in solid body, you can say, where the body is rigid and the actual particles will not move, like in a solid body. Say there is a metal rod and you're heating one end of this metal rod, then another end will also after some time will get hot, but here the material, the particles of this metal rod will not be moving, but they'll start vibrating, and because of that vibration the heat will they will vibrate, they will come in contact with each other. Because of this, ultimately the heat will reach from one end to another. This is called conduction, but here the particle will not actually move, only the heat will be transferred because they will be vibrating and coming in contact with each other. So the heat will transfer from one end to another end. So in conduction actual migration doesn't happen. Radiation, this doesn't even need the medium. In this also this doesn't happen. Reflection, anyway, it's not heat transfer thing. It happens for convection actually, in which actually the migration of medium particle happens. Like in case of boiling or heating a container of water. So there is a water container and it's kept on stove, okay? It's kept on stove and I'm heating this water. As soon as the water particles at the bottom gain energy from the stove, they go up, right? And the other remaining molecules now come at the bottom, and again they will also heat, they will also come again. This keeps on happening. So in kind of this example, actual movement of particles happen, and this is called convection method. So in convection method, actual migration of medium particles happens. So convection is the correct answer here. Now another, when current passes through junctions of two different metals, the evolution and absorption of heat is known as. So Seebeck effect, we know, it talks about conversion of Seebeck effect is that if there is temperature difference between the junction of two different metals, then it leads to voltage difference. Joule effect is something else. Thomson effect also talks about when there is a temperature gradient in a conductor and current is passing, then there is absorption and release of heat at those points in the conductor. But here the statement is, when current pass through the junction of two different metals, then evolution and absorption of heat. This phenomenon is known as the Peltier effect. This is known as the Peltier effect. Now the next question, in general, in which range of temperature the platinum resistance thermometer, the PRT that we were talking about just a while back, it can be used to find temperature? Okay, so we didn't discuss this, but this is a standard known fact that PRT is widely famously used because it can give temperature, we can measure temperature in a very wide range from -200 to 1200 degrees centigrade we can measure. That's why platinum resistance thermometer is widely used. So this is the correct answer here. Next question, which of the following statement is wrong in respect to the, again it's a PRT based question. So which of the statement is wrong with respect to the platinum resistance thermometer? It can measure the temperature of a given point of large body. It works nicely in a wide range of temperature. We have seen that its temperature range is minus 200 degrees centigrade to 1200 degrees centigrade. So this is true statement that it works in a wide range of temperature. Zero adjustment is not needed for thermometer. For any measurement equipment, actually zero adjustment is always needed. Temperature change as small as 0.02 degrees centigrade can be measured accurately in the range of 0 degrees centigrade to 630 degrees centigrade. This is also standard known fact about PRT. Actually, we'll discuss, as I told, we will discuss in detail the PRT in next week's lectures. But this fact is also true about PRT. So what is wrong here is that PRT can measure temperature of a given point of a large body. So as I had shown that PRT consists of a coil, okay, and that coil is like kept inside the body, and then there is some we measure the voltage and current and find out the resistance, and then we can correlate it with the temperature of this body. So this coil needs some time as well as some amount of heat to understand what to so that it will be able to detect some resistance and give us the value of temperature. So determining temperature of a particular point of a large body is not possible because the coil is not very small, it is like significant, and because of this determining temperature of a particular point of a large body is not possible. So this is the wrong statement about PRT. Okay. Next question is, which of the following has the negative temperature coefficient of resistance? So what do we mean by temperature coefficient of resistance? So we, as I told earlier also, and you must be knowing that for a metal or for any material actually, when we increase its temperature for any material, say, when we increase its temperature, there is change in its resistance. Change in resistance. If, for example, say that with the increase in temperature, the resistance is also increasing, then it is called positive temperature coefficient of resistance. Okay, and this happens for metals, that with increase in temperature of the metal material, the resistance also increases. This is known as positive coefficient of resistance. Thus, what will negative coefficient of temperature mean? It will mean that with increase in temperature, the resistance decreases. We know this happens for usually for insulators. But anyway, so this is what we mean by negative temperature coefficient of resistance, that with the increase in temperature, the resistance of the material is decreasing. So which out of these materials have negative temperature coefficient of resistance? So gold is a metal, that means it has positive temperature coefficient of resistance. Silver also is a metal, that means it also has positive temperature coefficient of resistance. Mercury also is a metal, it also has positive temperature coefficient of resistance. Carbon actually has covalent bonding. We know carbon has 4 valence electrons, right? And they bond with each other through covalent bonding. Thus, when if we have some carbon material, okay, carbon sample in any kind of shape and size, and we supply heat to it, okay, we are increasing its temperature, then these covalent bonding will break. These covalent bonding will break, and thus we will have more electrons for conduction. That means when we will apply heat, we will increase its temperature, the resistance will decrease. So for carbon, out of these four things, carbon will have negative temperature coefficient of resistance. So this is the correct answer here. Okay, now the next question is, okay, it's related to specific heat capacity, it seems. So the question is, two metals A and B are of specific heat capacities S1 and S2. So we have two metals, metal A and metal B. Their specific heat capacities are S1 and S2. They are mixed in the ratio of mass of 1:2, and then when we are mixing these two metals, they become some sort of alloy, and then we are heating that alloy to a temperature of 320 degrees centigrade. Now this mixture is put inside the water, which where the temperature of water is 20 degrees centigrade. When we put this heated alloy in this water, the final temperature of water becomes 50 degrees centigrade, means equilibrium, it reaches equilibrium and the temperature becomes 50 degrees centigrade. Now keeping all other parameters unchanged, if they are in the ratio of mass 2:1, so in one case we are considering they are in their mass, or they are mixed in the mass ratio of 1:2. Now we are talking about another case where their mixing ratio is in the ratio of 2:1 of their masses. Then the final temperature becomes 40 degrees centigrade. Find the ratio of S1:S2. Okay, first let's, since we can understand it's a question of specific heat capacity, and we know from the law of calorimetry, first for the case 1, where they are mixed in the ratio of 1:2 of their masses. So from the law of calorimetry we know heat released or heat lost, released or lost anything, heat lost by the alloy will be equal to the heat absorbed by water. Heat absorbed by water. Now we know the formula for heat transfer is mass, and mass of say, let assume we have not been given the mass of these metals, but let's say we have been given ratio, right? Let's say this mass of A is M1, mass of B is M2. We have been given that to make the alloy they are mixed in 1:2 ratio. That means for case 1, let's say the mass is M, then mass of B will be 2 times, right? So it will be 2M. So mass of first material times its specific heat capacity value and the temperature difference, plus mass of the second one. I can write it like this also. Mass of the second one, its specific heat capacity, and because they are made into alloy, the temperature difference value will be same for both of them. Now this equivalent to the mass of water. Here we have to ignore the heat taken by container, okay, and heat loss due to vaporization. We are assuming here that whatever heat was released by the alloy, everything is being absorbed by the water. So mass of water times the temperature difference for water and specific heat capacity for water. So here M1 is small m, S1 delta T plus M2 is 2 times M, S2 delta T, mass of water times delta T W SW. So from here, if I take out M common, okay, what I'll get is I'll take out M common and delta T common, then M delta T I'll take out common, then I'll get S1 plus 2 S2 is equal to, I'll put the values of this. So mass of water, we had taken 400 gram. We had taken 400 gram of water. And the temperature difference of water, initially the water was at 20 degrees centigrade, the final temperature becomes 50 degrees centigrade, means the difference is 30 degree centigrade, right? Yeah, the temperature difference is 30 degrees centigrade, and we have not been given the value. For time being, we'll just keep it like this. So from if I'll rearrange this, I'll get S1 plus 2 S2 equal to, this will be 12, no, this correct, 400 gram times 30 times SW. Yeah, I think it's correct. Divided by M delta T. Mass of these bodies, okay, anyway we don't know that, so mass I'll just keep it, but delta T we know. So they were heated to 320 degrees centigrade and finally it comes to 50, means they were heated to 320 degrees centigrade and finally they come to 50 degrees centigrade, means what will be this? This will be, this will be 320 minus 50 is 270. 270 times M. This will get cancelled. That means it will be 1200 divided by 27 M. This is one expression. Now we have case 2 also. Here even specific heat capacity for metal A is unknown, specific heat capacity for metal 2 is unknown, and this mass is also unknown. So we need another equation to be able to solve this. We ultimately need to find out the ratio of S1 and S2. So from the case 2, in case 2 we are making the alloy by mixing the metals in the ratio 2:1. Earlier it was 1:2. Now it is 2:1. So again, following this law of calorimetry, I'll directly write this time. So it will be M delta T. Now this time 2 times 2:1 it was, right? So it will be 2S1 plus S2 is equal to, okay, now again I think the amount of water kept is same, but the final temperature is different. It's 40 degrees centigrade. So the temperature difference will become 20 degrees centigrade. And again I'll just keep, oh, I forgot to, even this is there actually. This is also there, SW. And again here also the specific heat of water is there. So from this equation, 2S1 plus S2 will become 8,000 times this divided by mass is unknown, and delta T in the second case will be, it was 320 initially, now it becomes 40. It was 320, now it becomes 40. That means what will be this? 320 minus 40 means 280. So this will be 280 times M. This cancels. So this is another expression. Now if I'll divide, okay, let's call this equation 1, let's call this equation 2. Now dividing 1 by 2, if I'll do that, then what I'll get is, I'll get S1 plus 2S2 divided by 2S1 plus S2 will be equal to, what was it? Okay, we can divide it by 3 also, 3 4s. 12 9 by 27. The same we can do here. Okay. With 4 and 7 for the 28. Yeah. So it will be 400 by 9. Will be the SW's will be cancelled, but okay, 400 by 9 M. Here we have SW, and divided by, it will be divided by this, means where is my cursor? Means 7M divided by 200. This these ratios will cancel. We'll get 2 times. That means 14 divided by 9. Now we'll solve this and we'll get, if I'll multiply 9 to this side and 14 to here, I'll get 9S1 plus 18S2 is equal to 28S1 plus 14S2. And I'll try to solve this. It will be 28, okay, 18S2 minus 14S2 is equal to 28S1 minus 9S1. This will be 4S2 is equal to 28 minus 9 means 19S1. So I can get S1 by S2 will be 4 by 19. So the ratio of specific heat capacity for these two materials is 4 by 19. This is the correct answer. Okay, this was a good question on specific heat capacity. We have one more question, which is a metal weighing 4.82 gram was heated to metal weighing, mass of the metal is given, just 4.82 gram, was heated to the temperature 115 degrees centigrade, and it's put into 35 ml of water. So mass of water, we know 1 ml, we can take 1 gram, 1 ml is 1 gram, so mass of water we can consider 35 gram, and the water temperature is 28.7 degrees centigrade. The metal and water were allowed to come in equilibrium temperature, and that equilibrium temperature is 34.5 degrees centigrade. Assuming no heat was lost to the environment, means whatever the metal released, the same amount of heat was absorbed by the water. In assuming this, calculate the specific heat of the metal. Again, using the law of calorimetry, the heat released by metal will be equal to heat absorbed by water. Heat released by metal means its mass times its specific heat capacity times the temperature difference will be equal to the mass of water. This is mass of metal. Mass of water times specific heat of, here what I have written, specific heat of metal, here specific heat of water, and the temperature difference for water. Okay, so mass of the metal was 4.82 gram. Specific heat capacity we need to find out. Again, temperature difference 115 minus equilibrium temperature is 34.5, so 34.5 degree. Mass of water 35 gram. Specific heat capacity of water we are given 4.186 joule per gram degree centigrade, 4.186, and the temperature difference for water, initially its temperature was 28.7, finally it reaches to 34.5. 34.5 minus 28.7. Let's do, so this implies, what will be this? 4.82 times, look at this, 115 minus 34.5, that means 80.5 is equal to this side. Let me calculate. 35 times 4.186, okay, and that is 146.51, and this temperature difference will be 34.5 minus 28.7, that is 5.8. okay. From this, the specific heat capacity of the material will be 146.51 times 5.8, that means 849.758 divided by 4.82 times 80.5, that means 388.01. this will be 849.758 divided by 388.01. So what I'm getting is 2.19 joule per gram degree centigrade. So this is the value we are getting for this particular material. So this is the answer. Yeah, so thank you for joining for today's session. So this was what we discussed. Okay, let's have a recap. We discussed many experiments based on thermoelectricity and actually thermal property of any material. So where we talked about, let me just, so the coefficient of thermal conductivity, how to find out for a not so good conductor or a bad conductor using Lee's disk method. Then we understood the electrical equivalent of heat or Joule's equivalent of heat, its value, its constant, and how to determine it using a calorimeter setup. What is Dulong-Petit law and how to determine the specific heat of given solid metal using Dulong-Petit law. What is a thermocouple, what is Seebeck effect, and how to determine the Seebeck coefficient. Then we little bit only we talked about this PRT, platinum resistance thermometer, and in detail we'll be discussing it in upcoming week. Based on this, we did few previous year problems. So this was all about today's interaction session. Thank you. We'll see you next time. I'll stop the recording now. Okay.